Joe, where's Joe? Oh, hey, Joe, come on up. So next up, we have Joe Stein. So Joe is a student at Brown University. Anybody else here from Brown? Yeah, okay, I went to Brown too. Joe was the intern with us at Delphix last summer, where he worked on a ZFS project called Eager Zeroing, and I'll let him take it away. Thanks.
Cool, thanks, Matt.
Oh, let me give you that microphone doesn't work anymore, so.
All right. Hello? Okay, it's working, cool. All right, I guess I'll jump right in. As Matt said, my name's Joe. I worked at Delphix, and yeah, I worked on Eager Zeroing as my intern project. So the problem here is a certain storage provisioning technique on certain hypervisors, VMware, AWS, where you ask for a certain amount of space, you get that reserved immediately, but the actual blocks aren't mapped and allocated until the first access, or first read or write on that block. This is called thin provisioning or lazy provisioning. So this is really good for saving space up front if you have an expanding volume. It's also good for saving time up front because you don't have to wait for all those allocations and mappings to happen. But it's really bad for I/O speed later on in the system, in the system's lifetime. So AWS says you can see up to a 50% loss of IOPS. And VMware actually did an internal study of this. I've simplified it a little bit, but we can see about a 66% loss of IOPS there. So the performance hit is pretty bad on these first accesses. So there are two current solutions. One is pre-warming, which is basically writing to or reading from all the blocks on your volume before you use it, which can take up to several hours. This is according to Amazon's documentation, or more depending on your storage configuration. The other solution is simply to bite the bullet, to say, I don't want to wait all that time, so I'm going to accept this degradation in performance, but I'll be able to use my storage immediately. So the new solution that I worked on, ZFS Eager Zeroing, attempts to strike a balance between these two solutions, where it sort of does this pre-warming in the background so you can use your system immediately, but we get the eventual like 100% performance guarantee that pre-zeroing gives us. So I have a little graph here. In purple we have a pre-zero disk, so you can't use it for all that time until the process is done, but then you get 100% performance. With the bite the bullet solution, you have this sort of dashed blue line because we don't actually know where it goes. It depends sort of how you access your blocks. And with the Eager Zeroing solution, you get the availability that's, as I said, not given to you with the pre-zeroing solution. But eventually, once Eager Zeroing completes, you do have that 100% performance guarantee. So there are a few features of the Eager Zeroing project. One, it's controllable, so you can suspend, resume, cancel, start zeroing at any time on any virtual device. Two, it's seamless, so it doesn't interfere with other device config operations. You can add new devices, you can promote, you can make mirrors, and zeroing will continue through this if it makes sense. Of course, if you're removing a device and it's being zeroed, it's not going to continue doing that. It's isolated, so you can control the Eager Zeroing processes on different VDEVs independently of other VDEVs, and it's verifiable. So the Eager Zeroing process will report back to userland how far along it is, and not only will it tell you whether or not it's completed, but it'll actually tell you when it's completed. So we can know exactly when we're going to have that 100% performance guarantee. So I had a little demo. It had animations. So say we have a pool called my pool. It has one disk to begin with, C1, T1, D0, and we're going to add these two new disks and start Eager Zeroing them. So we do that with Zpool add. You've all seen that. The new command is Zpool Initialize. You give it a pool and optionally a list of disks that you want to start Eager Zeroing on. If you don't give it a list of disks, it'll just try to Eager Zero all of them in the pool. That's not what we want here because our first one has already been zeroed. And then when we run Zpool status, we see that our two new disks are being Eager Zeroed. So you can also cancel Eager Zeroing. So this is the controllability that I talked about. If we, say realize that the second disk has already been pre-zeroed or was thick provisioned or something, we can actually cancel the eager zeroing just by passing the C flag to Zpool Initialize. When we check our status, we see that the third disk is still being eager zeroed, but the second disk is no longer. And we can suspend and resume eager zeroing just by passing the S flag to suspend, and just to resume, we just pass no flag, so Zpool Initialize to the end of the disk, and it will pick up where it left off. Use case for this is, say your server's really busy on the weekends, so you don't want eager zeroing to be competing with bandwidth, like I/O bandwidth with other applications, so you suspend eager zeroing for the weekend and resume it during the week. Okay, so how does this all work? So I'm working with the example of a two-way mirror here, but this is extendable to pretty much any VDEV tree. So we spin up one thread per leaf virtual device, and we walk through the top levels metaslabs. So while we're actually doing this eager zeroing, we don't want any real allocations to happen on the metaslab because we don't want to overwrite user data. So we prevent allocations, which is the red metaslab. There are limitations on how many metaslabs you can actually mark off as unallocatable because we don't want our entire top level VDEV to be unusable. So that's a kernel tunable. So for each of those metaslabs, we walk through the free tree and we just write zeros to all the ranges in the free tree, translating for RAID Z as necessary. For freeing during zeroing, so if things are added to this tree, we don't really care because if something's been allocated, it's almost certain that something's been written there, and then the sort of pre-warming effect has already been taken care of. Cancellation and suspension are just a matter of stopping the thread, and resuming is a matter of starting up a thread. It finds where the last thread left off in this new piece of infrastructure called the per VDEV zap that's up in the MOS, and that's also something that I worked on this summer. Okay, so performance. So there's a lot going on this slide. So first, this is a graph of write throughput as observed from user land. So the procedure here was, well, first the bench was we had one 100 gigabyte spinning disk for each of these trials with a pre-zero disk, with an untreated disk, so the bite-the-bullet solution, the pre-warming solutions, and then this new solution, ZFS eager zeroing. And so we wrote as fast as we could for 3 minutes, waited for 4 minutes, and rinsed and repeated, and we got 4 sort of write periods here. So 4 interesting parts of this graph. So first we have these big spikes at the beginning of each write period. That's just because the ZFS write queue is filling up. So from user land, it looks like those writes went through instantaneously, but they actually haven't been flushed to disk. Once the write queue fills up, the spike ends. 2, so during our second write period, throughput has sort of stabilized. And as predicted, the pre-zero disk is doing very well at around 120 megs a second. The untreated disk, so the bite-the-bullet solution, is doing okay at around 70 megs a second. And the disk that's being eager zeroed is not doing quite as well at 50 megs a second. Again, this is because the eager zero writes in the background are competing with these writes from user land. So at around 15 minutes in, eager zeroing completes. And we see that the throughput on the eager zero disk actually shoots up, doesn't stabilize before the end of the write period. That brings us to our 4th write period, in which throughput has stabilized and eager zero has ended. And we see here that these 2 top lines, the pre-zeroed and eager zeroed solutions throughput, are comparable. And of course, the bite-the-bullet solution is still doing poorly down there. Okay, so the current status of the code is, so this per VDEV zap infrastructure that I mentioned briefly is actually shipped to GitHub on Delphix OS. We have 2 consumers right now, parts of VDEV removal that Matt Ahrens wrote, and this eager zeroing system. Stress testing and functional testing are also complete, but there were some SPA config locking issues that I was unable to resolve before I left for the summer. I think George is working on this. Yeah, cool. So hopefully those will be out soon. So future work for this project. So as we saw, performance is suboptimal before eager zeroing actually completes. So there are a few ways we can improve this. One is to weight eager zeroed metaslabs higher so that ZFS actually prefers to allocate from sort of pre-warmed metaslabs, then data actually written to those metaslabs will go through to disk faster. Two, we can throttle zeroing. So currently there's a kernel tunable that just says how many writes outstanding, or writes can be outstanding at any time from the eager zeroing system, but those go as fast as possible. If we implemented a scheduling system, kind of like what scrubbing does, sort of deadline, we could space out the eager zero writes and alleviate throughput competition that way. And third, this actually doesn't work very well for SSDs and SCSI because the controller thinks that we're actually filling up the entire disk with zeros. And so once the disk becomes full, performance degrades because it has to do all this remapping. So for SSDs, we can send trim commands to say, hey, we're actually not using those regions, and similarly unmapped for SCSI. And with that, are there any questions? Yeah.
I was just curious, did you guys ever do any benchmarking on like AWS?
No, so yeah, the performance benchmarks that I provided were VMware. I did not get to AWS. Yeah.
This is a question to a comment. On the samples plot that you deduplication at the block level, this would actually work as it would recognize as the old block, so we should if you're actually doing deduplication one data twice.
Right, right. Yeah.
And maybe another comment is, at Incento we've already done that trim work, and one mode of trim is deceptively similar to the eager zero stuff, so there should be quite a bit of overlap, and yeah, we will be upstreaming that fairly soon, so we could collaborate on simplifying all that code path.
Sweet. Any other questions, comments?
Thank you, Joe.
Thanks.